Question 8a. Let G be a group and A belongs to G. Prove that the mapping FA G to G defined by FAX equal AX for all X belongs to G is a bijection. Bijection mapping means 1 to 1 and onto. If we are able to show that FA is invertible, then we can conclude that FA is bijective mapping. Here it is given that FAX equals to AX. So FA inverse FAX is FA inverse AX. And this is A inverse AX. And which is A inverse AX. So that is X only. Next FA inverse X. FA A inverse X. A inverse X. A inverse X. That is X. Therefore, FA inverse FAX is equal FA inverse X, which implies FA is invertible. It implies FA is 1 to 1 and onto. Hence, FA is bijective. Question 8b. Give an example of an abelian group which is not cyclic. Here 3 examples are given. Any one you can write. First example, set of real numbers. Second example, set of rational numbers. Both of them are abelian group and they are not cyclic. Example 3, Klein's 4 group. It is also abelian group but not cyclic. Here first 2 examples are of infinite group and Klein's 4 group is finite group. The set of real numbers and set of rational numbers, both of them are abelian group which are not cyclic under the binary operation addition. Klein's 4 group has been discussed in details in another video lecture. If you are interested, you may watch that. The link has been given below in the description. Question 8c. Find the generators of the group Z8, binary operation addition here. For any k belongs to Z8, GCD of K8 is 1 if and only if K equals to 1, 3, 5, 7. Therefore, there are 4 generators. Did it. Question 8d. Let H be a subgroup of a group G. Define a relation rho on G by A rho B if and only if A inverse B belongs to H. Prove that rho is an equivalence relation on G. Also prove that for A belongs to G, the equivalence relation class of A is the left coset AH. What is the definition of equivalence relation? Rho is an equivalence relation of G if rho satisfies the following for all A, B, C belongs to G. Number 1, A rho A, that is called reflexive. Number 2, if A rho B, then B rho A, which is called symmetric. If A rho B and B rho C, then A rho C, which is called transitive. Now we will show each of them one by one. Here there should be one R. A rho A, both A implies A inverse A, which is actually E, and H is a subgroup of group G, therefore E belongs to H. Hence, rho is reflexive. Next, A rho B, both A implies A inverse B, both A implies A inverse B inverse equal B inverse A inverse inverse, that is B inverse A, which implies B rho A. Therefore, the relation rho is symmetric. Now let's take A, B, C belongs to G. Then A rho B, both A implies A inverse B belongs to H. B rho C, both A implies B inverse C belongs to H. Now let us multiply both of these, A inverse B, B inverse C. Then we will have A inverse B, B inverse C. B inverse is E, so we can write A inverse C, which will imply A rho C. Therefore, rho is transitive. Now we have to prove the second part of the question. Also prove that for A belongs to G, the equivalence class of A is the left coset AH. It is given that A inverse B belongs to H. Then we can write A inverse B H equal H. How? If H small h belongs to capital H, which will imply small h H equal capital H. Why? Because H is the subgroup of G. We know a theorem. If H is any subgroup of a group G and H belongs to H, then HH equals to H equals to HH. Now here we can take A in left hand side, A inverse B H A H. A will be there in left of H in the right hand side. Now A inverse BH is AH. A inverse is E, which belongs to H, EBH. So BH equal AH. Therefore, the equivalence class of A is the left coset AH.